Hello everybody. So I was hoping the test was going to be on Tuesday, which is why I kind of didn't make the video. Sorry about the delay, but let's get started. So in this particular video, I'm going to cover one practice test for the second test. There are three possible variations of how this test could end up diverging into, but we'll only be covering one of them depending on where it goes, and hopefully this should give you enough idea of how to tackle the other outcomes as well. All right, so without wasting any more time, let's get started. All right, so okay, so we have a particular let me just read it out first. So the marketing manager has contracted a web design firm to put together a new look for the company's website with the goal of improving the amount of time visitors spent on the website. The web design firm proposed two different designs, A and B. In order to assess the designs, the marketing manager designs an experiment where the visits to the website in a given hour were randomly assigned to each of the two designs, and the number of seconds that they spent on the site was recorded. There were 32 visits for the design A and 26 visits for design B. The box plot below are the resulting visit times spent on each design. Okay, that's fair enough. Now let's go into the test here. So let me just download the data here, open that up in Excel. Okay, so I'm just going to copy that, just like that. Okay, copy, Control C, and then I'm going to go into my SPSS and then right click, paste with variable name. Perfect. Now as you can see, both of these variables have been recognized as scalar variables here, with the which is represented by the yellow ruler or scale or whatever it is. The first data is a scalar variable, which is true. However, the second variable is designs is not a scalar variable. This is basically one represents design A and two represents design B. So this should not be a scalar variable. So let's fix that. Let's go into the variable view. Now in this particular test, let's drop the number of decimals to 0, okay, because that'll give you the answers in two decimal places, which is what you need for your output. And in the design variable, I don't need decimals for this either. Now the measure for the first one, I know the first variable is what is scalar. Okay, happened here. This is not supposed to have happened, but let me just delete these variables. Okay, the first variable is scalar. The second one is either group A or group B, which is a nominal variable, not a scalar variable, right? So I'm just going to put that into as a nominal. It's not ordinal either, because the order doesn't really matter. You can have B before A. It doesn't make any difference to your result. Now when we go to values here, 1 represents design A, right? Whereas 2 represents design B. Now this is not that important for you to do, but it will create less confusion down the road. So it's just to follow the best practice. Let's just follow this along. Let's go back to the test here. So if you click on this button here, it should toggle between design A and design B. Okay. Now we have, as you can see, we have 32 observations for A and 26 observations for B, which means that both the sample sizes are more than 10, which means that the first question, or to decide whether to go for the parametric or the non-parametric test, is pretty obvious. As you can see in this, the sample size for both of the samples is more than 10. So if you're asking, is n less than 10? No, it's not. It's more than 10, right? So we're going into this category. So we've checked the normality in this case. So let's go back to the question. So first, once I have the data transferred, I need to check the standard error. For design A should come as 0.578, and for design B as 0.689. So to check that, I'm going to go into Analyze, Descriptive Statistics, Explore. I'm going to drag my time variable in my dependent list and the design into my factor list. So if I go into plots, I'm going to check histograms, and then I'm going to check normality plots with test as well. All right. So in this case, I'm just going to start continue. And okay, there you go. So the output's there. So let's look at the output. So in this case, The standard error for A is 0.578, which is correct, and the standard error for B is 0.689, which is also correct. Therefore, that's pretty good. So now let's look at the first question. Complete the following considering the means of the data. For design A, it's 71.63. I got 71.63 here. Okay. I don't know if that's... This is not very comforting here in this case. Let me just see what we have here. It's 71.62500. Okay, this is very rare, and this is probably why SPSS has rounded it up as 71.62, whereas I have 71.63. I mean, if this happens, I mean, this is like a 1 in a million chance you'd be this unlucky, but I guess we'll just have to see how it goes. So the mean for design B in this case is 70.96. So let's put that down, 70.96. And the confidence interval for design B is between 69.54 and 72.38. Perfect. Okay, so in this case, by examining the 95% confidence intervals for overlap, complete the following sentence. At the 5% significance level, the visit time for design A, so this is for design A, in this case, the maximum for design A is actually more than the minimum for design B, right? And clearly there is an overlap between these two. Or in this case, the minimum for, no, the maximum for design B is actually more than the minimum for design A in this case. So there definitely is an overlap in this particular case. So since there is a pretty strong overlap, as in like the confidence interval for A is actually within the confidence interval for design B, so there definitely is an overlap in this case. So since there is an overlap, we can't tell whether there is a significance difference. So at a 5% significance level of significance, the mean visit time for design A may or may not be, you know, significantly different to that of design B based on, you know, the confidence interval analysis. Now let's look at the skewness of the data. So the skewness statistic, in this case, we have a skewness statistic of let's say Q1 0.727. Okay, with a standard error of 0.414. Oh my god. Okay, so if I multiply this by 2, I'm going to get 0.828, which is actually less than the skewness statistic, which means that design A is significantly skewed, right? So the absolute value of the skewness statistic is not less than 2 times the standard error. Therefore, data for design A, data can be considered to come from population that is, in this case, it's definitely skewed, and the sign here is positive, it's not negative, therefore it's going to be positively skewed. Let's look at design B. The skewness statistic is 0.376. The standard error is 0.456. If I multiply this by 2, I'm going to get 0.912, which is more than the skewness statistic in this case. So since this is actually more than that, design B is actually symmetrical, is more consistent with the symmetric data. Now the normality test, which is down here. Now in this case, we have the design A has a significance level of literally 0. Okay, so it's definitely not normal. We have a Shapiro-Wilk test that has 32 degrees of freedom and a test statistic of 0.804. Okay, so we're looking at this one. Don't use this. All right, this is the Kolmogorov test. So this is not what you're looking for. You have to go with this one here. I hope you can see the pointer here. And the case for design B is that we have a p-value of 0.204, and that's correct, which is more than 5% or 0.05. Therefore, it is reasonable with a normality assumption. Now, in this case, we have let's go back to the slideshow here. One of them is normal and the other one is not. So in this case, we're going to go with no, it's not normal. Now, one sample size is more than 30, the other one is not, right? So in this case, we have to use the non-parametric test in this case. Does that make sense? Hopefully it does. If not, just put it in the comments and I'll probably try to explain it slightly better. So both of the samples must be greater than 10. Sorry, must be greater than 30 for you to opt for this particular option, even though one of them is not symmetric. So you're going to end up using the non-parametric test anyways. All right. So in this case, let's go back to the test assumptions. So in this case, for this I need to run the Levene's test. To run the Levene's test, I'm going to run the t-test by itself. So I'm going to go into analyze, compare means, independent t-test. Time goes into my variable, design goes into my grouping variables. I'm going to define group 1 was 1 obviously, and 2 is 2, right? This should not be there on default. It's there because I just ran this test just before I made this video, but it should not be there. So you should put 1 and 2 as your variables, and I'm going to run the test. So in this case, the Levene's test this is the one right here, the test for equality of variances. I have a f statistic of 0.656 and a p-value of 0.421, which is more than 5%, which means that I can assume that the variances are equal. So since the p-value is more than 5%, I cannot reject the null hypothesis. In this case, the application of the Levene's test indicated that the equality of variances is a reasonable assumption in this case. Now, in this case, we have one sample that is not normal and it's not symmetric either. So we cannot use the parametric tests or the first two options. So we have to go for the non-parametric, which is the Mann-Whitney test. So I'm going to have to run this particular test. So to run this test, I'm going to go into analyze. It's a non-parametric test. It's independent samples. So I'm going to customize the test. Time goes into my test variables and design goes into my grouping variables. All right, and in the settings, I'm using a Mann-Whitney 2 sample test. That's all you need to do, and you need to run the test. So once you run the test, the results should appear as follows. So it's taking so much time, my god. Okay, in this particular case, this should be enough information here. The application of the Mann-Whitney test indicated that the dash. All right, so let's just fill the bottom line first. The p-value here is 0.356. 0.356. This is pretty high, right? This is more than 5%, so you cannot reject the null hypothesis. In this case, since it is more than 5%, that indicated that. So the Mann-Whitney test looks at the distribution. All right, so there's a couple of differences here. You have to understand that the parametric test compares the mean. Okay, the Wilcox test compares the medians, and the Mann-Whitney U test compares the distribution. So in this case, you're going to check distribution. Design A is significantly, now in this case we have a p-value that is more than 5%, so it's actually not significantly different to that of design B, right? So in this case, the Mann-Whitney U coefficient in this case is this value right here, 357.500. Okay, that's the test statistic in this case. It's 357.500, and that should be the end of the test. Hopefully this kind of made things slightly more clear. If you still have any more confusions, you can put it in the comments, or maybe the fastest way to reach me is on Facebook, but you could just try to put it in the comments. I'll try to check it before I go to bed, and hopefully I'll be able to answer your questions. So yeah, good luck. Let me just check, and yeah, there you go. All right, see you tomorrow, guys.